So for this, that is the rate of mass of A in, we get the term NAZ at Z is equal to 0. For the rate of mass of A out, we get the term NAZ at Z is equal to Z plus delta Z. A correction to be made. This NAZ, that is the rate of mass of A in the system, is at Z, not at Z is equal to 0. So the rate of mass of A out is NAZ at Z is equal to Z plus delta Z, and the rate of production of A due to the homogeneous reaction can be written as K1 triple prime CAS into delta Z. Now we put all the three terms into the shell mass balance. So we get a equation as NAZ at Z minus NAZ at Z plus delta Z plus K1 triple prime CA delta Z into S is equal to 0. This becomes our shell mass balance. Now what we have to do first is we will firstly divide the equation by S into delta Z. By doing so, we get the equation as NAZ at Z by delta Z minus NAZ at Z plus delta Z by delta Z plus K1 triple prime CA is equal to 0. Now we multiply the whole equation by minus 1. So we get. So you might think why we multiplied the whole equation with minus 1. This is done to fulfill the condition of out minus in. Anytime or always we need to fulfill the condition where we do a difference between the out and the in of the property which we are working with. In a similar way, here also, as we are working with the flux or the rate of mass of A that is going in and out, so just in order to do that in the out minus in condition, we multiply the whole equation with minus 1. So by doing that, we receive the equation as NAZ at Z plus delta Z by delta Z minus NAZ at Z by delta Z minus K1 triple prime CA is equal to 0. Now, taking the limit Z tends to 0, we write NAZ at Z plus delta Z by delta Z minus NAZ at Z by delta Z can be written as dNAZ by delta dZ. So as we saw that limit del Z tends to 0, NAZ at Z plus delta Z minus NAZ at Z by delta Z is equal to nothing but dNAZ by dZ. So putting this back into the equation we had, we receive NDNAZ by DZ plus of K1 triple prime CA is equal to 0. This is the reaction we get to. Equation we get to. Also, now we assume that the concentration of A is very small in the molar flux equation that we had already derived. So, the convective term is neglected and we are left with a molar flux term in the z direction, because we had already assumed that the concentration is varying in the z direction. So we get NAZ is equal to minus DAB dCA by dZ. So now this is the total molar flux. So what we can do is we can substitute this equation of NAZ into the above equation of the shell mass balance. So by putting it over there, we get DAB D2CA D square CA by DZ square minus of K1 triple prime CA is equal to 0. So this is the reaction which we get to when we put NAZ as minus DAB into dCA by dZ into the shell mass balance equation. And this happens because the total molar concentration C is almost or virtually uniform throughout the liquid. Now we come to the step where we need to put in boundary conditions that we had already written and solve this above differential equation which we received. So earlier we had seen 4 different boundary conditions, but to simplify the differential equation which we have received, we come up to a conclusion that we can use the 2 boundary conditions. The first one is concentration at a surface is specified, that is XA is equal to XA naught, and the second boundary condition being the mass flux at a surface is specified, that is NAZ is equal to NA naught. So we now write the boundary conditions as boundary condition 1 at Z is equal to 0, CA is equal to CA naught. Boundary condition 2 at Z is equal to L, NAZ is equal to 0. So this boundary condition happens because dCA by dZ is equal to 0. Now, further explaining the boundary conditions, we have selected the first boundary condition of Z at Z is equal to 0, CA is equal to CA naught, because the concentration of A at the surface of the liquid layer B is considered to be CA naught, that is a constant, and the second boundary condition of at Z is equal to L, NaZ is equal to 0. This, the second boundary condition, is because no A diffuses through the bottom of the container at Z is equal to L. So due to a very less or no A diffusing into the last or the lowest point of the beaker, that is Z is equal to L, the term of dCA by dZ turns out to be 0, due to which when we put this in the molar flux equation, where Na is equal to minus dAb dCA by dZ, since this term turns out to be 0, the whole NaZ term turns out to be 0. So this is how we end up at NaZ is equal to 0 at a boundary condition of Z is equal to L. So these are the two boundary conditions which we will use to solve the differential equation that we have received as dAb into d square Ca by dZ square is minus K1 triple dash Ca is equal to 0. Now we see that on applying or putting the boundary conditions, these two boundary conditions, we get a lot of variables, due to which solving of this differential equation becomes quite difficult and tedious. So in order to simplify that and get to a simple equation where we can solve the equation easily, we do one thing. We multiply the whole equation with a term of L square Ca naught into dAb. This term, by multiplying this term into the whole equation, we get the whole differential equation in terms of dimensionless variables. By now getting the equation in terms of the dimensionless variables, it becomes very easy for us to solve the equation. So the equation turns out to be d square gamma by d zeta square minus phi square gamma is equal to 0. So we all might be wondering what gamma and zeta and phi means. They are nothing but where gamma is equal to Ca by Ca naught. This is a dimensionless concentration. Zeta is Z by L, which is a dimensionless length. and phi is nothing but root over of K1 triple prime L square by DAB. This is a dimensionless group which is otherwise known as the Thiele modulus. We will get to know more about the Thiele modulus and understand what its importance is in this concept of mass transfer in homogeneous chemical reaction.
So, the Thiele modulus is generally applicable only for the heterogeneous reactions, but the homogeneous reactions with gradients where the diffusion gradients or the transport resistance are there, we can use the Thiele modulus to describe the external or special constraints on reactions. So, this Thiele modulus describes how reactions and diffusions interplay even in systems that aren't strictly heterogeneous. Now our dimensionless variable equation is there. We need to apply the dimensionless boundary conditions for this case. Unlike in the previous equations, we use the boundary conditions which are different from this. We need to use the boundary conditions which are dimensionless. So, our dimensionless variable equation is d square gamma upon d square zeta square minus phi square gamma is equals to 0. So, in this equation, we will apply the dimensionless boundary condition as first is at zeta is equals to 0, the value of the gamma will be 1, and the second boundary condition is at zeta is equals to 1, the d gamma upon d zeta is equals to 0. So we need to apply this boundary condition in this dimensionless variable equation so that we can reach to our final result. So after applying the boundary condition, firstly, our equation is upon d square gamma upon d zeta square minus phi gamma is equals to 0. So it is square, by the way. So the general solution of this equation is gamma is equals to C1 cos h phi zeta plus C2 into sin h in bracket phi zeta. So we will apply the boundary conditions as at zeta is equals to 0, the gamma will be 1. So after applying this boundary condition, we get C1 1 is equals to cos h while putting gamma as zeta as 0, we get cos h as 1, so it will be C1 only, and by putting the zeta here in the sin h equation, sin h, it will become sin h 0, and it will become sin h in 0 is equals to 0, so this term will be 0. So it will remain with only 1. C1 is equals to 1. The next boundary condition is at zeta is equals to 1, the d gamma upon d zeta is equals to 0. So we need to take the differentiation of this equation. So we can write this equation after putting the value of C1. Gamma is equals to cos h phi zeta plus C2 into sin h phi zeta. So we need to take the derivation dt upon d zeta is equals to the derivation of cos h zeta, phi zeta is phi into sin h phi into zeta, and the derivation of sin h phi zeta is cos h phi zeta, and before that phi will be there. So zeta will be, we will put the zeta as 1 and dt by d zeta is equals to 0. So it will become phi sin h, it will be phi only, and it will become cos h phi. So C2 is equals to sin h phi upon cos h phi. So these are the two constants which we get. We will put these two constants in our equation. So gamma is equals to cos h phi zeta plus sin h phi upon cos h phi into sin h phi zeta. So this is the final equation which we get after putting the boundary conditions. Now we know that gamma is equals to Ca upon Ca naught, which is the dimensionless concentration. So after further evaluation, this equation can be converted into gamma is equals to cos h phi zeta minus sin h phi zeta upon cos h phi. It can be further simplified to cos h phi 1 minus zeta upon cos h phi. So now here is the simplified form. We can put the definition of gamma as Ca upon Ca naught, that is the dimensionless concentration, and also we can put the value of this phi, that is Taylor modulus, and zeta. So after reverting it to the original notation, we get Ca upon Ca naught is equals to cos h in bracket k1 triple prime L square upon dap in bracket 1 minus z by L upon cos h in square bracket k triple prime L square upon dab. This is the final concentration profile equation from which we can draw the concentration profile for our problem. Now, after solving the concentration profile, we can get the other quantities as well, like average concentration. So for evaluating the average concentration in the liquid phase, we need to use the formula as Ca average upon Ca naught is equals to 0 to L upon Ca naught into dz upon 0 to L into dz. So this equation will give, after putting the value of Ca by Ca naught in the equations, so we know the value of Ca by Ca naught is what? Cos h in square root K1 triple prime L square upon DAB 1 minus Z by L bracket close upon cos h into phi. So we will put the value of Ca by Ca naught in this equation, and after solving this we get Ca average upon Ca naught is equals to tan h phi upon phi. So this is the equation for the average concentration. Moving forward, we need to find the molar flux as well, because it was also included in the objective of our question. So to get the molar flux, we know NaZ at Z is equals to 0 is equals to minus dAB dCA by dZ at Z is equals to 0. So after taking the gradient of this, we get NaZ by Z is equals to 0 is equals to Ca naught dAB upon L into phi into tan h phi. So this is the required flux profile. We can write it as molar flux profile. We can draw it like it will be these two lines. It will vary. Z is equal to 0 and Z is equal to L. It will go from, at the surface it will be Ca naught, and at Z is equals to L it will decrease in this way. So this is the required flux profile. Now you can see we have achieved all our objectives. Now this result shows how the chemical reaction influences the rate of absorption of gas A by liquid B. You may wonder how the solubility Ca naught and the diffusivity dAB can be determined experimentally if there is a chemical reaction taking place. First, K1 triple prime can be measured in a separate experiment in a well-stirred vessel. Then, in principle, Ca naught and dAB can be obtained from the measured absorption rates for various liquid depths L.